Hi and welcome back. So in the previous video we worked until the point where we showed the relationship between investment and capital accumulation, and in doing so we showed the evolution of capital stock, and we said the evolution of capital stock was given by this relation here. So this relation, we concluded that it tells us that the capital stock in the beginning of a certain year, say for instance year t plus 1, that is kt plus 1 here, is equal to the capital stock at the beginning of year t, meaning that it is equal to the capital stock of the previous year, which is still intact in the new year, which is the t plus 1 year. So that is represented by the capital stock of t plus 1 capital stock of t adjusted for depreciation. So we said depreciation, capital stock that is depreciated is represented by 1 minus depreciation. This shows the amount of capital stock that is still intact, plus the new capital stock put in place during year t. So that is the investment that was made during the year t. So that's the new capital stock. Okay, given this, we can now combine the relation between output and investment and the relation between investment and capital accumulation to obtain the second relation we need in order to think about growth. That is the relation from output to capital accumulation. So the first thing to do is we have to replace investment by its expression above here. So we replace investment by this expression of itself, and then divide both sides by the number of workers in the economy in order for us to look at these factors in terms of workers. So we look at capital per worker, investment per worker, and output per worker. To do that, we get this expression here. So this expression tells us that capital per worker in the beginning of year t plus 1, that is capital per worker at year t plus 1, is equals to capital per worker at the beginning of year t adjusted for depreciation. O is the capital per worker of year t that is still intact in year t plus 1, meaning that it is adjusted for depreciation here, plus investment, which is now given by its expression of this, plus investment per worker during year t, which is equals to the savings rate times output per worker during year t here. So this comes from this investment being expressed in terms of savings rate times output per worker. The next step is to expand this term here and move the capital per worker in year t to the other side. So in doing so, this is what we get after reorganizing it. So this basically tells us that the change in capital stock per worker, that is capital stock in year t plus 1 minus the capital stock of the previous year. So it's the change in capital stock per worker, basically represented by the difference between the two terms on the left, is equals to the savings per worker represented by this first term here on the right, minus the depreciation represented by the second term here, right? So that is the change in capital stock per worker is equals to the savings per worker minus depreciation. So how we got to this expression is simply working out this portion of the function of the term here. So this times that is going to give us the K over K capital per worker that came out to the left, and this one that remains is going to come from this part times that. Okay, so this new expression is quite straightforward. What it means is that the difference between capital stock that we have, for instance, in 2020 and the one that we had in 2009 is simply what has been invested throughout 2019 and what remains of what we started 2019 with. So the difference between capital stock in two terms is simply the difference between investment and what has been depreciated of what has depreciated of the old capital stock. So this is straightforward. It also gives us the second relation, that is the relation between between output and capital per worker. Okay. So what we've done so far is that from the production side, we have seen in equation 11.1, this one, in this equation, how capital determines output. And from the savings side, we have seen how from equation 11.2 and this one, how output in turn determines capital accumulation. So what we're going to do now is put the two relations together and see how they determine the behavior of output and capital over time. So that's what we do next. So we combine equation 11.1 and equation 11.2 to see the dynamics of capital and output over time. Substitute equation 11.2 into equation 11.1. This is what we get. So in essence, what we have done is replaced output per worker in equation 11.2, output per worker here, in this equation, that's output per worker, by its expression in terms of capital per worker, shown by equation 11.1. So by its expression of that. So in so doing, we put capital per worker here in the place of output per worker, or rather where output per worker was before. So this new equation tells us that the change in capital from 1 year T to year T plus 1, that's the change in capital per worker, is equals to investment during year T here minus the depreciation that happened during year T. This new relation here describes what happens to capital per worker. So that is, the change in capital per worker from this year to next year depends on the difference between two terms. That's the difference between investment. That's the investment that has been done in the first term, and the depreciation that has happened to the capital per worker that was existing in the first term as well. So looking at this relation, you should notice that if investment per worker exceeds depreciation per worker, that is, if this part here exceeds this one, the change in capital per worker, the outcome here between these two, will be positive. So if investment per worker is greater than depreciation, then the change in capital stock per worker will be positive. So capital per worker will increase. And if investment per worker is less than depreciation, that is, the depreciation per worker is greater than the investment, the change in capital per worker is negative. So capital per worker increases. Or rather, sorry, capital per worker here decreases. It will fall if the depreciation is greater than the investment. Equation 11.3 together with 11.2 are critical to the solo growth model because they contain all the information required to understand and analyze the dynamics of capital and output over time. And the easiest way to interpret them is to use a graph. We do this in this graph here, where output per worker is measured on the vertical axis here, and capital per worker is measured on the horizontal axis here. So this figure, the same relation as the one we looked at before, the relation between capital per worker and output per worker represented here. So output per worker is still a function of capital per worker. So here on this curve, output per worker increases with capital per worker, but because of the decreasing return to capital, the effect is smaller the higher the level of capital per worker gets. We have to look at is this one of investment per worker, which tells us that investment per worker, this one, has the same shape as the production function, but is lower by the factor of the savings rate. So this means that investment per worker increases with capital per worker, but at a decreasing rate and lower than output per worker. So if you remember, we said savings, capital increases output, and savings rate determines how much of the output or income is saved. So the higher the capital, the higher the output, and the higher the output, the higher the savings that has been saved. The higher the total savings. So when capital per worker is already very high, the effect of a further increase in capital per worker on output per worker, and by implication thereof on investment per worker, is very small. The straight line in our figure here represents depreciation. So depreciation per worker increases in proportion to capital per worker. So the relation is represented by the straight line, hence the straight line. And the slope is represented by the depreciation rate. As capital per worker increases, moves to this direction, all three factors, investment, output per worker, and depreciation, increase. So to the left of this capital per worker star, investment exceeds depreciation. So as you can see, investment here is greater than the depreciation curve until a point where the two are equal. So they're only equal in that point. And to the left, depreciation exceeds investment exceeds depreciation, and capital per worker increases. So from any point below here, below this, for as long as investment is greater than depreciation, you can keep increasing capital per worker. And to the right, depreciation exceeds investment, and capital per worker must be decreased to any point greater than any point above this point here, and this point is known as the steady state point, here where depreciation is equal to investment. So let's conclude on this. So the steady state of the economy is the state at which capital per worker and output per worker are no longer changing, but rather remain constant. It's a steady state change in capital per worker is equal to 0. So given the steady state of capital per worker here, the steady state of output per worker can also be represented by this function here. So steady state of output per work is equals to that of capital per work. Thank you.